Hey everybody, this is Mr. Lowry. Today we had a guided notes on proving angle relationships. Now this is actually the section of your textbook where these ideas come from, so if you want to go back and reference your textbook you can. But I wanted to go over some important ideas with you in this section, and one of them was how to prove a theorem. Okay, so let me give you a quick example of a theorem. This is one of the theorems we're going to prove today. If two angles form a linear pair, then they are supplementary. Okay. Notice that the theorem is like a conditional statement. In other words, it's an if-then. It assumes something and then concludes something, right? And when you're trying to prove a theorem, the first thing that you have to do is you have to figure out what can you assume and what are you trying to prove, okay? So this step-by-step stuff right here, how to prove a theorem, will help us to be able to set up the proofs that we're trying to do today. Okay, so this is a fill-in-the-blank notes that we did. If you weren't here today, you can go in and grab the kind of the filled-in copy here. But I would also recommend that you go through this video and go through these proofs so that you understand how it works. Okay, so whenever you're trying to prove a theorem, which again is like a mathematical if-then statement, the first thing you have to do is you have to identify the hypothesis and the conclusion of that statement. So the hypothesis of the statement comes right after the if part. Okay, so this is called the hypothesis. If we were like labeling this, we would call this P. And then the part immediately following the then, the word then, is called the conclusion. We would call that Q if we were doing like detachment or syllogism or something, if we were labeling it. But in this case, what we're doing is we're trying to do a proof. And so the hypothesis is what in our proof is the given part, and the conclusion is the part that we're trying to prove, the statement we're trying to prove. Okay, so that's what it says here in number 1. So once we've identified that, what we're going to do is we're going to draw a figure that represents the information that we're given, this information. Okay? So in this case, the given information is that we have a linear pair. Okay? Now step 3 says don't assume anything about the figure other than what's given. Okay? So I don't want to pick particular angle measures or anything like that. I just want to draw a basic linear pair. Okay, so step 2, draw a figure that represents the given information. Step 3 kind of goes along with step 2. Don't assume too much. Don't try to assume too much. So I'm just going to draw a quick linear pair. Now it doesn't have to look specific. There doesn't have to be a specific angle measure. I'm just using this tool right here just as like a ruler to make straight lines. Okay, so there's my linear pair. Okay, haven't assumed anything other than what's given, just that I have a linear pair. Okay. All right, step 4, label the figure according to the given information and be generic as possible so that your figure represents as many cases as possible. Don't use specific measurements unless specifically stated in the given. So I don't want to label this like 140 degrees and 40 degrees. We don't want to do that. We want to leave this as generic as possible. So I'm just going to call this angle 1 and this angle 2. All right, step 5 is to rewrite the given and the proof statements, these two guys, but using the figure, using the new labels that we chose. So the given is that we have a linear pair. In this case, what we're going to say is that angle 1 and angle 2 form a linear pair. So it sounds like we're being kind of specific because we're talking about 2 specific angles that we drew, but the point is that we didn't pick specific measurements. Right? We don't know what these measurements are. And so in that way, it still stays generic enough to be a proof. Okay, now in the proof statement, this is just going to be basically this part, the conclusion, but with our angle labels. So angle 1 and angle 2 are supplementary. Okay. Now we have it set up. Okay. we have to decide what kind of proof we're going to use here, and we have different options. We have two-column is our most traditional style. We also talked about paragraph proofs and flow proofs, but we didn't talk about those in a ton of detail. So what I want to do today is I want to use the different formats here to help prove these theorems so that you can kind of understand how those different formats work. So in this case, we're going to do a paragraph proof. Okay. Now, we still want to make statements and then justify each one of those statements. We still want to use theorems, postulates, properties, and definitions as we go to justify our statements. We just don't have the same structure. So the best thing to do if you're trying to do a paragraph proof is talk the proof out first. Maybe talk it out to your brother, sister, mom, dad. It doesn't matter if they understand it or not. The point is to give you an opportunity to think through it. So prove it to your dog, prove it to yourself in the mirror, whatever you want to think. Just talk through it first, and then you can kind of write your ideas from there. All right, so let's kind of talk through this together. The only thing that we have to work with is that we have a linear pair. And so we have to go back and think about what the definition of linear pair actually is. And the definition of linear pair is that it's two angles that are adjacent, right? So they share a side. And then the non-common side, these two sides are the non-common. This is the common side, these are the non-common sides. The non-common sides of those two angles form opposite rays, or in other words, a straight line, or a straight angle. Those are all kind of equivalent, okay? So if I just draw the non-common sides of angle 1 and angle 2, that's what it looks like, right? Because this is the common one. So notice that that is opposite rays or a straight angle. So I'm just gonna, this is just kind of a, you wouldn't normally write this on the proof. This is just for us as a reference. So opposite rays, or in other words, a straight angle or a straight line. Those are all basically equivalent definitions. There's a place in your book when it talks about opposite rays that just like kind of off to the side, it's hard to notice, but it says opposite rays are the same as a straight angle. Okay, so here's our angle, and okay, what do we know about straight angles? They measure 180 degrees. Okay, so the gist of this proof is like this. Angle 1 and angle 2 are a linear pair. Therefore, their non-common sides form a straight angle. The measure of a straight angle is 180 degrees by the definition. And since the measure of angle 1 and the measure of angle 2 have to add up to the measure of the straight angle by the angle addition postulate, the measure of angle 1 plus the measure of angle 2 must be 180. And since if they add to 180 they're supplementary, then angle 1 and angle 2 are supplementary. So that's just me talking it through. Now essentially that's what we're going to write. We're just going to write almost like a conversation how this proof goes. Okay, so let's start with where we started. We started with the definition of linear pair. We knew angle 1 and angle 2 formed a linear pair from the given, so we're just going to talk about that definition. So angle 1 and angle 2 form a linear pair, or let's start there. Let's not do too much information at once. Okay, they form a linear pair. So what that means is that the non-common sides of angle 1 and angle 2 form opposite rays or a straight angle. By the definition of linear pair, the non-common sides of angle 1 and angle 2, I'm going to use some abbreviations here, and you're welcome to do the same, form opposite rays or a straight angle. By definition of straight angle, the measure of a straight angle is 180 degrees. We also want to talk about the fact that 1 and 2 together has to be 180, and that's going to be the angle addition postulate. So the measure of angle 1, actually let me go back and I think I'm going to use more words instead of symbols since this is a paragraph proof. So what we want to say is the sum of the measures of angle 1 and angle 2 must equal the measure of the straight angle and then we want to put y, and that's the angle addition postulate we talked about last week. The angle addition postulate says that if two angles are adjacent, their measures, when you add them together, form the measure of the bigger angle. So we actually have 3 angles here. We have angle 1, angle 2, and then this big straight angle that they combine to, basically. So the measure of angle 1 and the measure of angle 2, when we add those together, have to equal the measurement of the straight angle, and that's the angle addition postulate. Since the measure of angle 1 plus the measure of angle 2 equals 180, we just stated that they have to equal 180. They are supplementary. Actually, I'm going to add one thing, sorry. I'm going to go back here and add that these were 180 degrees. We already said that, but just to be specific. So now we said that the sum of the measures of the angles 1 and angle 2 must equal the measure of the straight angle, which is 180 by angle addition postulate. Since the measure of 1 plus the measure of angle is 180, they are supplementary, and that's by the definition of supplementary. I'm going to use another abbreviation here. You can do the same. All right, so that's a paragraph proof. Now, again, it seems kind of hard to write, but it's really just like if you can talk it through, you can write the paragraph proof. That's all it has. That's all it is. So if you're like, I don't know how to write a paragraph proof, I would just say to you, explain what's going on to me, and you would explain it to me, and we would talk it out, and then I'd be like, great, write that. Okay, so angle 1 and angle 2 form a linear pair. Therefore, the non-common sides of angle 1 and angle 2 are opposite rays or a straight angle. The measure of the straight angle is 180. The measure of angle 1 plus the measure of angle 2 has to equal the measure of the straight angle because of the angle addition postulate. Therefore, the measure of angle 1 plus the measure of angle 2 equals 180, which means they have to be supplementary by the definition of supplementary. Okay, so that's the proof there. Paragraph proofs are a little bit more wordy. They're a little bit less structured, but notice that we still have statements and justifications because I used like the angle addition postulate, and I use definition of linear pair, and I use definition of supplementary. So I'm still using definitions, postulates, properties, things like that as I go. All right, cool. So that's proof 1. Okay, we're going to do the same thing here for a couple more proofs, and this will help you get the information you need for your homework. All right. Now, I may ask you, on a future test or quiz to kind of prove some of these theorems or prove parts of these theorems. So even though this isn't part of the homework, you should definitely know how to do these for the future. So study these proofs, know these proofs. You're going to be accountable for this information. Okay, the next proof is Theorem 2.6 in your textbook. And the way that the theorem is worded in your textbook has a few extra words, and there's actually two different parts to the proof, but we're going to kind of simplify this a little bit. The congruent supplements theorem basically says angles that are supplementary to the same angle are congruent to each other. Okay, so going back through our steps here, the first step we want to do is we want to identify the hypothesis and the conclusion so that we know what we're trying to prove and what we can assume. So this is not in an if-then statement yet. So I'm going to say if angles are supplementary to the same angle, then they are congruent. So kind of forcing this to be an if-then statement so that I can call this the hypothesis, which is what I can assume or what I'm given, and this is going to be what I'm trying to prove. So assume the P, prove the Q, basically, or assume the hypothesis, prove the conclusion. All right. Step 2 is to draw a figure, but step 3 says don't assume any information that we don't have. So we want to draw supplementary angles. We actually need 2 angles that are supplementary to the same angle. Okay. Now we don't want to make any extra assumptions, so be very careful here. It doesn't say anything about the angles being specific angle measures. It doesn't say anything about them being adjacent to each other, right? So we don't want to assume too much. We want to be as generic as possible. So I need 2 angles that are supplementary to the same third angle. All right, let's see what that one looks like. So I'm going to draw 3 angles here. So here's angle 1. Okay, and then I'm going to draw a second angle. Angle 1 needs to be supplementary to some angle, so I'm going to draw them so they look relatively supplementary. Okay, we'll call that guy angle 2. And then we need a third angle because I need 2 angles that are supplementary to the same angle, right? So I need another angle, and it's probably going to look pretty close to angle 1 because what we're trying to prove in the end is that angle 1 and angle 3 are congruent. So let's kind of talk this through. If 2 angles are supplementary to the same angle, then these 2 angles must be congruent to each other. Okay. Now we don't want to use specific measurements, but just to understand this, let's put some specific measurements and then we'll erase them. So we're not going to use them in our proof. They're just going to help us understand what's happening here. Let's say that this angle is 140 degrees. Okay. Now I don't know that that's actually the case, but let's just say for the sake of argument that it is 140. If this were 140 and these 2 were supplementary, this guy would have to be 40 degrees because they have to add up to 180. That's what supplementary means. Okay, so if these 2 are supplementary, then this is 140, this is 40. Okay, now think about this for a second. If this angle is also supplementary to angle 2, it has to be 40 as well because there's only one number that I can add to 140 to get 180. Right? So if this angle is supplementary with 140, it's 40 degrees. If this measure is supplementary with 140, then it's also 40 degrees, which means that these have to be congruent to each other. Okay, now again, when we do our proof, we don't want to use specific angle measures. That was just for us to kind of help us understand what this is saying. Okay? So if these 2 are both supplementary to angle 2, then they have to be congruent to each other. Okay, now that's what we're going to write for our next step. We're going to write given. Okay, we got angle 1 and angle 2 are supplementary. And in the same given, we also know that angle 2 and angle 3 are supplementary. Okay, what we're trying to prove then is that angle 1 is congruent to angle 3. All right, now we're going to do a 2-column proof in this one. And it just so happens that this 2-column proof is very, very similar to a proof that we had on the blue assignment from last Thursday. It was a 2-column proof, just basically practice proofs with segments and angles. So if you want to, you can get that assignment out as a reference because this is going to be very, very similar to one of those, or 2 of those problems, excuse me. All right, so on this side, in a 2-column proof, we have statements, and over here we have reasons. I'm going to use S and R. Okay. Also, the first thing that we always write down is the given. So angle 1 and angle 2 are supplementary. I'm going to abbreviate here. You're welcome to the same. Same line, same statement. We'll also say that angle 2 and angle 3 are supplementary. And that's just part of the given. Okay, now we have to build our proof down to here. Now I've done this proof a couple times before, so you wouldn't necessarily know how many steps it's going to be. but it's going to actually be 5. And our last statement should be the statement we're trying to prove. Okay, angle 1 is congruent to angle 3. So we got to figure out how to fill in the gaps here, only using postulates, properties, or theorems that we've already proven, or definitions. Okay, well, let's go back to that definition idea. What does supplementary mean? Well, the definition of supplementary is that the measures add to 180. So just from this definition of supplementary, we know the measure of angle 1 plus the measure of angle 2 equals 180. And since we have two different statements here, we can also say the measure of angle 2 plus the measure of angle 3 also equals 180. Those are both going to be for statement 2. They're kind of the same idea. And the reason for that is the definition of supplementary angles. Right? They add to 180. So that definition alone puts me into these two equations, which is great, because as soon as I have equations, I can use properties of equality, right? We can use substitution, we can use addition, subtraction, all those different ideas, okay? In this case, what we're going to want to do is a substitution, because angle 1 and angle 2 add to 180, and angle 2 and angle 3 add to 180, and so we can replace this 180 with what 180 is equal to. In other words, we can replace this 180 with the measure of angle 2 plus the measure of angle 3, and that will give us the measure of angle 1 plus the measure of angle 2 equals, and again, instead of 180, we're going to replace that with the measure of angle 2 plus the measure of angle 3. And since we replace something with what it's equal to, that is the substitution property of equality. Okay, now let's think about where we're going. We want to show that angle 1 and angle 3 are congruent. Well, here's angle 1 and here's angle 3, and notice that I have the measure of angle 2 on both sides of the equation. Now, I don't know what the measure of angle 2 is specifically. It could be 60 degrees, it could be 120 degrees, I don't know. But whatever it is, it's the same on both sides. And so whatever that measurement is, I'm going to subtract that from both sides, and that will give me the measure of angle 1 equals the measure of angle 2, measure of angle 3. That's the subtraction property of equality. We usually use it when we're solving equations, kind of like this. When we want to get x by itself, we can subtract the same number from both sides. Okay, that's also true even if I have variables. So in this case, I could subtract 3x from both sides. So it actually doesn't matter if we know that number or if it's an unknown number. As long as it's the same on both sides, we can subtract it. So the same thing is true here. We're subtracting this unknown measure from both sides because we know it's the same on both sides. Okay? All right, now these statements are very, very similar. This one says the measures of the angles are equal. This says the angles are congruent. And that the transition there, we just use the definition of congruent angles. The definition of congruent angles is angles whose measures are equal. And definitions can go in both directions. So if two angle measures are equal, then the angles are congruent. If two angles are congruent, then their angle measures are equal. So this is the definition of congruent angles. And that's our proof. Okay? So a 2-column. Now again, this is very, very similar to a proof you've had, and the whole idea was to prep you guys for proofs that we're going to be doing today with practice. Okay? Video's getting a little on the long side, so I'm going to stop it here. In the next video, I will come back and we will do the vertical angles theorem, and then we will do some homework examples. Thanks for watching.